Okay, good afternoon, everyone. My name is Keith Suderman. I'm from the Language Application Grid project. As you might be able to tell by the name on the slide, I feel a little bit like a fish out of water here. I think I'm the only one here using Galaxy, not for genomics or bioresearch. We're doing natural language processing with Galaxy. So I'm just going to tell you a little bit about the LAPPS Grid project and how we're using Galaxy and what we would like to do in the future. The Language Application Grid, we're developing a framework for natural language processors. We would like our users just to be able to go out and take a black box application to be able to do natural language processing tasks, things like information extraction, question answering, machine translation, speech recognition. Anybody that's tried to talk to Cieri or give their car directions or tell their car to phone someone knows that those fields need quite a bit of work yet. There's many other NLP applications out there as well. We just recently started using Galaxy as our workflow editor and workflow engine, and we're mostly interested in the workflow editor. We want our users to be able to take components, drop them onto the workspace, and then connect them with little noodles without having to write any Python code or Java programming. Now, when I've been talking to people here, people always seem a little bit incredulous that we're using Galaxy for NLP problems, but actually we have quite a bit in common. We process large amounts of mostly text data. The data needs to be run through a pipeline of processors of some sort where the workflow is application dependent. In our case, the workflow for a question answering system is going to be different than the workflow for machine translation or text summarization. And basically we're all just searching for patterns in the data that we have. Another thing in common is that the processors that we use typically haven't been designed with the idea that they're going to be connected in some sort of workflow. So the output from one tool is not going to be suitable input for the next tool. So we need to shim our tools somehow so we can connect them together in the workflow editor. We do have some differences as well, of course. You guys work with genomes and proteins. We work with, and I tend to think of genomes as being, relatively large data sets, where we work with millions of small texts. A tweet is 140 characters long. Even a large novel is only about half a megabyte. The data itself, as I said, you've got genes and proteins. We've got Twitter and emoji. People are thinking up new words all the time. You've got the four proteins, A, C, G, T. Nobody's going to come along and say, hey, let's start using B now. If that was actually done, whoever came up with that would probably win a Nobel Prize for it, whereas the June 2016 update to the Oxford English Dictionary added 2,000 new entries to the dictionary. So human languages evolve very rapidly. Also, interestingly, most of our processors are web services that are distributed around the globe. So running Galaxy in a high-performance compute cluster doesn't really make a lot of sense in our use case because for us, the network is the bottleneck. We really want a big, fast network connection to connect our services. So this is what an NLP pipeline will typically consist of. The first steps are typically always the same. We need to do segmentation, identify sentence boundaries in the text, split words or split the text into words. And you might think that this is a simple task, and you would be wrong. There's a large amount of disagreement on how tokenization should be done, what a token is, how do you tokenize gonna, woulda, coulda, or shoulda, woulda, wanna. And even simple things like contractions. Is don't one word or is it two words? But once we have done sentence splitting, we can assign part of speech tags, and that's usually enough to do sentiment analysis, determine if a Yelp review is good or bad. We just have a bag of words, assign a positive score or a negative score to each word, sum them up, and do we get a positive or negative result? Once we've got the part of speech tags, we can start identifying entities, names of places, locations, dates and objects. And that's usually typically all Google needs to do to extract documents on the web for you, or as you type in the search bar, it's correcting your spelling or suggesting a completion for your query. Then we can do further parsing for syntactic structure and semantic analysis. If you've got something like John sold the book to Mary, well, selling is the action, John is the agent, Mary is the recipient, and the book is the thing that's being sold. So we need to be able to identify those things. And once we have those relations, we can extract them and start building models for them for machine reasoning systems, inferencing systems. Once we've got co-reference detection, co-reference is just identifying when two mentions in the same text refer to the same object. If an article mentions Barack Obama and later on it mentions the President of the United States, well, they are referring to the same physical entity. So we can do product or document summarization, topic analysis, machine translations. Now, the language application grid, what we want to do is provide interoperable access between a wide variety of tools and resources. As I said, the tools are not usually engineered in a way to talk to one another. And we want to be able to pipeline these things in black box services. We're also providing an open advancement framework. I'll talk about this a little bit later, OAQA, Open Advancement for Question Answering System, which is being developed by Carnegie Mellon. And we've got really two types of interoperability problems we need to look at. There's syntactic interoperability, just getting the formats of the tools to be interoperable. We use JSON-LD, JavaScript object notation for linked data. I don't know how many people here are familiar with RDF, but it's very similar to RDF. And we can enforce the structure of this data with JSON schema. And we also have semantic interoperability, which probably isn't a problem for genomics research, but it's a huge problem in natural language processing. People might not even agree what the agents are supposed to be for a particular verb to sell, or what a noun chunk is, or what a verb chunk is. So there's a large amount of disagreement in the researchers over the semantics of what we're doing. We've got a number of collaborations and projects going at the moment. We're federating with grids around the world in Japan, Thailand, China, and Europe. We've recently received a Mellon grant. It says on my slide here that we have a proposal in. Well, we have just been notified that we have received that Mellon grant to develop a trust network between the Clarin, which is in Europe, the Clarin network, and the language application grid, so we can log in with in common Internet 2 standards, and they can be assured that when somebody logs in that we know who they are and that they belong to a research institution or a commercial enterprise, whatnot. We're also being used by the DARPA Lorelei project, which is for under-resourced languages. If you're working in English or French or Mandarin Chinese, it's very easy. There's lots of data, there's lots of tools, there's lots of people working in it. But for some of the under-resourced languages, it's much more difficult. There's no data, there's no tools. We are also providing a multi-day course in NLP projects for government analysts, and we're also being used for graduate and undergraduate computational linguistic courses at Carnegie Mellon, Brandeis, and University, or Vassar, I should say. Now, one of the big problems that has faced the NLP community, and it's exactly the use case that Galaxy was developed for, is reproducibility and sharing. A great deal of work in the NLP world has gone into reinventing the wheel. It's always more fun to invent a wheel than use somebody else's, as well as sharing data, and that's mostly due to IP, intellectual property constraints. It's really hard to reproduce somebody's results when you're not allowed to use their data. So we need to provide an open way to share the data, get permission to share the data, and provide the mechanisms to do that. So I don't know if you can see this slide, but here's a common workflow. We've got some tools from GATE, which is the General Architecture for Textual Engineering, some tools from Stanford NLP, at Stanford University, of course, and OpenNLP, which is an Apache project, and of course they all produce different output formats that we need to connect together. And so we've provided shims where if two tools don't speak the same format, we can convert between them. But if we do have two tools that do speak the same formats, so here our gate tools, they exchange an XML format, and we let them speak their format to one another and only provide the shims when needed. The other thing we like Galaxy for, of course, is for visualization of our data. Here's an example. You probably can't read it. I'll pull this sentence up again a little later where it's a little clearer. But here we can see the part of speech has been colored. Each part of speech tag has a different color, and we can see the relations where objects, subjects, and predicates have been identified and what they are modifying. As I mentioned, Carnegie Mellon University is working on the open advancement for question answering systems, and this was actually used by IBM when they were developing their Watson system. They would work in a 2-week cycle where they would develop code for 2 weeks, freeze the code, evaluate it, and identify the components that were introducing the most errors. So they would know what parts of the system to work on. They would identify the parts, work again for another 2 weeks, freeze the code, and evaluate again, and continue on. And so this is what open advancement would look like in the LAPPS grid, where we've got 2 pipelines, 2 workflows where we're going, and in each step of the workflow, we're collecting statistics and doing an evaluation at the end of the pipeline. Then we can go in and tweak the little components, rerun the pipeline, and see if we're making things better or worse as we go along. Now, we would like to actually provide some feedback or, some payback to the Galaxy community and the genomics bio community. Galaxy contains a large number of tools for analyzing data, and we have a large number of tools for extracting and processing unstructured text. And by unstructured text, I just mean things that aren't in XML documents that have sentence boundaries and token boundaries already marked up. We've just got free-form text flowing. So what we would like to be able to do is, say, parse all of PubMed, PLOS, Biomed, and whatnot, and extract relations that then can be fed back into Galaxy tools. I don't know if I have enough time for my machine reasoning tutorial. Probably not. So we'll just skip through these. I was going to talk about machine reasoning, but we'll come back to that if we have to in a time. So here's an example of once we were able to extract some relationships. I believe this is written in Klingon. Binding to GTP causes a conformational change of the RAS protein that puts RAS into the active state. I'm certain that must mean something to someone here. As I said, it's Klingon to me. But that doesn't matter. The computer doesn't understand. I always say the computer is literally as dumb as a bag of light switches, because a computer is literally a bag of light switches. So the first thing we have to do is go through the sentence, identify the verbs and the predicates, the subjects and the objects, and how they relate to one another. So we can see the parse at the bottom. And this is the sentence on my earlier slide that we were visualizing in Galaxy, and just sort of a more simple output there. So we can start parsing these. We'll run it through the Stanford parser and a pathway extractor, and we can see that GTP binds to RAS, and we can add that to our data model, and then we can go on to the next sentence and see GT-bound RAS binds to the RAF protein, and we can add that to our model. And we can build up these models of predicates, subject, predicate, object, and build that up into a data model that can be used by inferencing systems. So as I said, some of the potential work we would like to do is to feed this model that we have extracted back into Galaxy tools somehow. And we're very interested in finding collaborators to work with in that goal. For example, the Galaxy 101 tutorial has the question, which coding exon has the highest number of single nucleotide polymorphisms on chromosome 22? And the Galaxy tutorial says, oh, that's simple. And we laughed and laughed and laughed, because if you were to ask Cieri or Google that question, it's not going to come up with the answer. I did ask Cieri that question, and what you get is the Galaxy 101 tutorial page. You don't get a coding exon as the answer. What we'd really like to do is ask Cieri that question and have it return either the Galaxy pipeline, or better yet, have Cieri run the Galaxy pipeline and give you the top coding exons, whatever a coding exon is. So the first thing we need to do is parse that question. Again, like we need to find the subjects and the objects and the predicates. Here the predicate is have. We're looking for something that has something. We're looking for a coding exon that has something. And in particular, we're looking for a coding exon that has the most number of SNPs on chromosome 22. So we need to do a number of things. First, we need to figure out what data we need to solve that question. And then we need to figure out the processing steps required to answer that question. And again, the tutorial says, oh, well, that's easy. Well, that's easy for a human, because a human brings all sorts of knowledge to the table, and it's easy for somebody that has a PhD in biology, not for the average person. So the first thing we need to do is identify where the coding exons come from, what data set contains that, what data set contains the SNPs, and then the steps we need to actually answer the question, that we need to join the coding exons with the SNPs on some common column, apparently column 4, but how do we know this? It needs to be encoded somewhere in the system. The rest of it is then relatively straight simple. Once we've joined it, we need to count, because we're looking for the highest number, so we can deduce that we need to count the number of SNPs per exon, sort them, and then return the top 5. And now Cieri is able to answer our question for us. And I think I have just enough time for a few questions if anyone is interested. Or I could go back and do Machine Reasoning 101. Only one, though.
So parsing papers, that would be very interesting, but what would be even more interesting, if, do you think that you can write something, some kind of a tool, if I give a sort of a textual instruction to Galaxy, sort of get these 2 data sets and run that tool with these parameters, please do it 5 times and so on. Do you think we can sort of create workflow out of that in Galaxy right away?
You mean,
that would be much more useful than parsing papers in my opinion.
Yes, and that would actually be much easier than parsing papers. If you were to give it a human description of the workflow that you wanted, it should be able to then analyze that and come up with the workflow from the human description. Parsing papers is really for something like IBM Watson. Like if you were to ask IBM Watson that question, it wouldn't be able to answer it unless it was expressed somewhere in a paper. It's not able to synthesize the question. But you could give it a description of your pipeline in a human language and have it construct the pipeline from that. I could see that as being very doable.
I'll talk to you more after.
So no direct question to natural language processing, but I'm always impressed for what Galaxy can be used. And I'm wondering, how get you know to Galaxy in your kind of research area, and how complicated was it to convince your colleagues to actually put that effort in a Galaxy environment that is more likely only used for scientists or biological scientists? Or
where did we hear for it, and how hard was it to convince people to use it? I had actually heard from it at an NLP conference called LREC, Language Resource Evaluation Conference. Someone else there was using it. We had taken a look at it, and we weren't quite mature enough at the time, but we since developed and started using Galaxy, and it was very easy once we took a look at Galaxy and did a quick prototype to convince everyone to do it. We were just at the last LREC just a few months ago, and there's actually been quite a bit of uptake of Galaxy in the NLP community. So it's very easy to convince other people to use it once they see it in action.
Hi. So I have a couple of questions too. 2 questions. One is negation, and if you take any approaches to that where somebody says this does not have something like this, and just if that's something you guys can deal with.
I'm sorry, I couldn't hear the question.
Negation. Oh, am I not close enough to the microphone? Negation. Are you dealing with negation when you do the parses? Where there's a, basically it says it is not involved in or does not have. Is that pulled out?
That's quite easy to do. It's things like, oh, I really love that, when they're being sarcastic. Sarcasm, you know, if it's explicitly said, negation is very easy to do. If they're expressing negation through something like sarcasm, that's almost impossible to do.
Yeah, that would be difficult. And then within the biological community, there's a whole group of people who do nothing but read papers. They're biocurators trying to extract the information and put it into computable form. That's where most of the NLP work has been done. And that's very goal-oriented, like does this paper discuss gene X? And you know, have you guys, because like you noted, the language is somewhat arcane, is it possible, have you had much experience working with these rather jargonistic areas?
We haven't ourselves, because we are actually just building the framework, not actually using our framework. We don't, eat our own dog food yet. But the students at Carnegie Mellon are actually working on that. There's a competition called BioAsk, where they parse PLOS and biomed papers, and then are expected to answer questions based on information in those papers.
I have two questions. Very fascinating. So anyhow, how do you have your tools available for everyone? Are they open source or whatever you are doing, or it's still closed?
No, everything we do is open source. Everything we write is released under an Apache 2 license, so it's completely open source and available on GitHub. Now, some of the tools that we wrap are not. They will either be closed source or they will have limits on their use. Same with the data. I meant to mention the collaborators we're working with, but the Linguistic Data Consortium, for example, is basically a clearinghouse for data. And to get data from the Linguistic Data Consortium, the LDC, you have to be a member, you have to have paid the dues. Their LDC lawyers will have sent you a contract that you actually have to physically sign and send back to them. So everything we do is open source, but we also provide some tools that are not.
And last one, can you think that you can use it for voice recognition and voice pattern in reading sentiments? Actually, I found it fascinating. So basically, I could have my phone stream to a galaxy and tell me if I love somebody and stuff like this, or if the relationship is ending. It's kind of cool based on, but can you do voice recognition? Can you transfer that too?
We don't do that right now, but one of our colleagues, it's actually the Steve Cassidy at Alveo in Australia. He's the one that introduced me to Galaxy, and that's actually one of the topics they are working on, I believe, is to take audio, transcribe it, and then process it there. So that sort of falls into one of the NLP tasks. Speech recognition is to first recognize the speech, convert it to text so we can run it through Galaxy. So we're not doing it ourselves, but it is being done by other people that are using Galaxy.